Swayam Prabha. Digital India. Educated India.
Gentlemen, let's continue our discussion on this one-dimensional problem. The weak formulation including the boundary term. And we have derived up to this point in the last class. So let's continue this one. So here what, just recall, we have this term coming, the boundary term, two terms. This is x is equal to L minus x is equal to 0. And together with this 0 to L domain integration of dwi by dx, ae du by dx, and then this term is because of the axial force, distributed axial force, and then this is actually the boundary condition. So if you carefully examine these various terms, so and try to eliminate some of them. For example, at x is equal to L, so you see that there is ae du by dx, which is occurring here, is also appearing here. W. So that means that that's appearing, but then there's a wi prime here. And so by choosing wi prime is equal to minus wi, okay, so it is not very difficult. So because wi is a set of functions, a complete set of functions, and then so wi prime also is supposed to be a complete set of functions. So they can be chosen in such a manner that one is negative of the other. So we are not losing any generality here. Okay, so if that is the case, then you can see that this term and this term can be cancelled, right? Okay, so these two terms can be cancelled, and then what else is left is this one here, wi ae du by dx at x is equal to 0. So if you choose the, for example, if you choose wi as a Galerkin weighted residual method, say wi is equal to psi I as in Galerkin method. So what is this? This is going to do. So if you recall, so that means that this psi I has to satisfy the boundary condition on the left side. Actually, we have taken the boundary condition only on the right side. So the one on the left side is still to be satisfied before we start this weighted analysis, right? So that means that this is assuming that u hat here satisfies the left side boundary conditions before we use it here. So what is that? So if you recall, so that u hat, if you, well, I didn't put it here. So u hat is really aj psi naught plus aj. So psi naught is anyway 0, and psi j is supposed to be 0 on the left side. So that means that the trial functions which we are choosing here are anyway or 0 on the x is equal to 0 boundary condition. So if that is the case, so psi I is 0 at x is equal to 0. So this is the trial functions. Okay, So there's 0. So that way, so this second term here also goes to 0. So what is left then? So let's look at what is left. So what is left if you collect, then we are left with dwi by dx ae du hat by dx, and what else? So we also have this one wi q dx, and then we also have wi prime. We'll take it to be minus wi, and then we multiply with p, and so we have minus wi times p. Obviously this is still evaluated exponential, right? So this is still, so this and this together are still remaining, so they still have to be evaluated x is equal to L. So this is the simplified weighted residual statement, and let us recollect these things and then put it in the form of algebraic equations. So let us, one thing is that wi will set it equal to psi I as appearing in the u hat. And of course here psi naught is 0 because psi naught is supposed to satisfy non-homogeneous boundary condition. And we don't have non-homogeneous boundary condition here. U is 0 anyway at x is equal to 0. So we are neglecting that. And so if this is the case, then so this can be now simplified as d psi I over dx ae, and here this is d dx of aj ij dx, and so this is the integral 0 to L. So this is the first part, and the second part here psi I to, oh, there is of course there's a negative sign that's appearing here. I'm sorry, there's a negative sign here. There's a negative sign here, minus wi p evaluated. Wi means psi I at x is equal to L, and this is 0. Okay, so this is, let's collect the terms properly on the left and right side. So there's a negative sign here, there's a negative sign here, and so what we do here is recollect. So you can remove this minus and a minus here and a plus there. So let's just recollect it here. And this is a d dx, we take it inside. This is minus, and this will take it to the other side. I and minus. Oh yeah, this is plus actually. This is plus here because wi. So you can see here. So this is negative, and then there's a plus here. So there's a plus here, and this is how it looks like. Okay. And so we can rewrite this one as aj, and this will collect it. This is psi I ae d Ij by dx. This is this part. And on this side, we have same thing. We continue to be okay. So this is the final algebraic equation. Let's put it in the matrix form. This is J is equal to. So in the matrix form, so such as K times A, where A consists of A1 up to AN. Okay, so what is Kij then? Here, so it is nothing but integral 0 to L d I by dx Ae d Ij by dx. So this is the Kij coefficient, and followed by the one on the right side will be I dx plus I p evaluated at x is equal to L. Okay, so finally this takes a very nice simple shape where Kij is nothing but d psi by dx, Ae d psi j by dx integrated 0 to L, and then there's also a term Q here, distributed force, and then there's a bounded term here, still it's existing here. So that means that this term should be evaluated by at psi I is equal to x is equal to L. Psi I is actually a function, and then its value at x is equal to L, that's what's required to be put into this one. So everything has been done here. Only thing is that just to recall what is the choice of you had here choice. What are the choice of the functions of psi j? What is just psi1, psi2, and if you want to make a choice of these things, what is the choice? If you take polynomial terms, for example, then what is the psi1, psi2? So these have to be something in terms of x or L. Okay. So only what are the things that need to be satisfied by the C in this weak form? So these psi i's need to satisfy only the other condition on the left side only. On the left side, we have the boundary condition that displacement u hat is equal to 0 at x is equal to 0. So this is what is required. Whereas on the right side, the applied force equal to P. So that is anyway has been taken into the weighted residual statement. So we need not satisfy that. So this has to satisfy only the left boundary condition. So that means that at x is equal to 0. So what are the polynomial terms which we can possibly assume is x by itself, and then x squared and x cubed. So this is a complete set in a systematic manner, and as you go on increasing all the way and tending to infinity, so any function may be represented. Okay, so just for the sake of completeness here, say if you just take one term, one-term solution, for example, then you have only K11, and K11, so if you put 0 to L, so then here d dx of psi 1, so that is 1 here, and AE, and again d dx of psi 1, again 1 here. So this is nothing but AE multiplied by L, right? What about B1? So B1 is, what is that here? So you have x times q here, dx 0 to L, and then x times p at x is equal to L. So this is x times q. So B1, if you continue, so B1, if you take q to be constant, so you can take x squared by 2, and square by 2 times q, and here this x into p, x was psi 1, and then this whole thing need to be evaluated at x is equal to L. So it is simply L into p. Okay. So this is what one-term solution is. So that means that this u hat is simply, what is that? Simply B1. In fact, here, if you want to calculate A1, so it is nothing but B1 by K11, and u hat is simply and taking 1, so we take A1 times x, where A1 is given above. Okay, so this is, you can also do this with 2 terms. Okay, if you take 2 terms, then the size of k will be 2 by 2. If you take 3 terms, so the size of k will be 3 by 3, and you have to solve for A1, A2, A3. Okay, so this is how we solve this one-dimensional problem using the weak form, taking the boundary condition into the weighted residual statement. So now what we do is that let us try to extend it to 2 dimensions. That's where actually the real application is, because one-dimensional is only for the sake of illustration. So now let's do it for 2D. How this taking this boundary term into the weighted residual statement is going to affect our algebraic equation. So let us take 2D example. So 2D example is of course slightly involved and slightly longer. And let's just take the heat conduction, which is the steady state heat conduction problem. So in this, so as we keep drawing, we have so here in this part of the boundary on gamma phi, we have phi is prescribed, and in this part of this thing, Q is prescribed to be Q bar. This is the heat flux leaving the thing, and so we have the governing equation, so which we keep writing here. And this is the governing equation where, of course, this K here is the thermal conductivity, which we keep writing. So please don't get confused this K with that K. And the boundary conditions are phi is equal to phi bar on gamma phi and minus k dou phi by dou n is equal to q bar on heat flux boundary condition. Okay, so this is the problem as stated here, and let us write down the weighted residual statement, which includes the boundary term also. So the weighted residual statement will be as usual. So we'll take the weighting function Wi and take this. Okay, we can take k inside. So here the conductivity, if you want, you can keep it inside, or you can take it this side also. So then here, what is that? The boundary term which we want to take into the weighted statement is Wi prime, and which is the one which we want to take into the weighted statement. So there are two boundary conditions, phi is equal to phi hat. So, well, these are the ones, phi hat, which we are assuming. And so that means that the phi hat has to be equal to phi bar. And so this part of the boundary condition is not difficult to satisfy. So that means that we assume that it is satisfied before we put it into this weighted statement. So the only thing that's left out is this one here, and that is k times dou phi by dou n plus 2 bar, and this is integrated over gamma. Okay, so here this has to be integrated over gamma q. Only this need to be integrated over the boundary. That's where this flux boundary condition is defined. Okay, as I was saying, so that this boundary condition on gamma phi part of the boundary here is not difficult to satisfy. So that we assume that the phi hat satisfies that before we put it into this one, and the only thing that's left out is the gamma q boundary condition. So let us do this. So what we have here, we need to do the partial integration. So let us take one term by one term. So let's take one term, the first term. This term where we have Wi dou square phi by dou x square over. So using our partial differential equation thing, so what we have here is that the term here, which the first one which comes as a boundary term here is gamma. So that is nothing but Wi k dou phi by dou x times n. Next. Okay, so I need to explain some of these things. I'll just explain these things by doing I'll just explain these things. Keep forgetting putting hat. Okay, for 2 dimensions, so this is how the integration is performed. So that means that this partial integration of this one using your Green's lemma, okay, using Green's lemma. So what we get here is that this partial integration k dou square phi by dou x square becomes k dou phi by dou x times nx. So what is this nx? So if you have a boundary here, so there is an outer normal here and then it has 2 components nx and ny. So this outer normal has nx and ny as the directional cosines, nx and y components, and so that means that here this is dou phi hat by dou x times nx also will be there times d gamma over the gamma, and then there is another boundary integral which is as the derivative will come on wi dou x, and then the derivative on phi will reduce, so k dou phi by dou x. So this is the first term. So similarly the second term, will be wi k dou square phi by dou y square dx dy or d omega. So this d omega here is dx dy. So I'm sorry, here dx dy, I have to keep writing. So this can be written as the boundary integral wi k dou phi by dou y times ny here times d gamma, and this follows the same lines as earlier. Okay, so sometimes I'm writing it d omega, or it's actually 2 dimensions dx dy, so you can write it as dx dy. So this is how the second integral looks like, and then that is followed by an integral wi times q, and followed by another integral here on gamma q. Only thing which you have to appreciate at this moment is that this gamma here is the complete boundary of this domain. So that means that it consists of both part of the phi prescribed, so that's gamma phi, as well as the gamma q here. That is, both are included in this. So if you want, we can write this as gamma phi plus gamma q. Okay, so now these are the terms, 2 important terms I expanded. So we can collect them, okay? We'll collect them and write it in this manner. So we'll collect this term and this term. So let us collecting the terms. So what we have here is an integral on gamma. So we'll take wi out, and we have k dou phi by dou x nx plus k dou phi by dou y and y, right, on gamma. So this is the 2 terms. And then we have a term on omega, so which is dou w by dou x k dou phi by dou x plus similar term here so this is the term on domain. Of course, there's a minus here. Sorry, there's a minus here. And apart from that, we have some term on Q. So that's WIQ. And then we have this boundary term as given on gamma Q, and that is given as Wi prime K rho phi by rho n plus Q bar. Okay, so this is how we collected all the terms. So this partial integration is, of course, again, I'm reminding, is by the application of Green's lemma. So an integration in 2 dimensions, partially integrated over a bounded term and this thing. Okay, all right. I think I'll stop here because these are the ones which need to be further simplified, and then we need to write it in a very concise manner, and we'll do that, and then we have to see how the terms gets cancelled here. Okay, I think I'll stop here. We'll continue it in the next class. Okay, bye.